detection of protein using seedless synthesized gold nanorods. First of all, my outline. Oh, sorry. So surface plasmon resonance, SPR, is a label-free technique used to with a high potential in the diagnostic area, especially when a signal amplification strategy is used to in order to improve the limit of detection. So we report here a simple method to enhance the limit of detection of the well-known protein bovine serum albumin by attaching gold nanorods. So we use BSA, bovine serum albumin, to conjugate it, the obtained nanorods, as a model of serum protein for different biochemical studies, and our goal was to enable detection of very low concentration of the biomolecules. Also, we used the finite element method to explore the potential enhancement of the SPR signal by adding the BESA conjugated nanorods on SPR metallic layer. And finally, the simulation as well as the SPR results confirm that the limit of detection of the BSA can be enhanced almost 10 times. First of all, we synthesized gold nanorods using a seedless surfactant mixture based on acetyl trimethylammonium bromide and bromosalicylic acid, an aromatic additive, which has the ability to altering the surfactant, cationic surfactant micellization. So 10 milliliters of solution containing the cationic surfactant and the aromatic additive were first of all dissolved in warm water at 60 Celsius degrees. After that, the solution was cooled at 30 Celsius degrees, and then there were added slowly chloroauric acid, hydroquinone, silver nitrite, and then small volume of sodium borohydride. And the reaction was left for 3 hours in dark room. After this, there was a purification step, and the obtained nanorods were subjected to conjugation, to BSA conjugation. This is the schematic representation of the seedless synthesis. So after the preparation, the nanorods were subjected to different to different or subjected to different characterization techniques. First of all, the morphological characterization. We revealed we obtain monodispersed gold nanorods having the aspect ratio 4.67 nanometers, in length almost 32 nanometers, and in width 7 nanometers. Also, the obtained nanorods were subjected to zeta potential measurements, and we obtained very nice stability, 106.64 millivolts. Also, after the conjugation, the obtained zeta potential was not so great, maybe due to the fact that the partial cover-up of the nanorods with the protein. Also, DLS measurements were performed, and there revealed the transverse and the longitudinal size bands before and after conjugation of the nanorods. So after the conjugation, there is an increasement especially in the case of transverse size bands, which can be which is maybe due to the effect of the BSA conjugation, especially BSA linkage, especially at the end of the nanorods. Also, the nanorods were subjected to UV ultraviolet spectroscopy, and we present in these graphs the BSA UV spectra, and also the nanorods spectra before and after conjugation. So before the conjugation, the transversal peak located at 515 nanometers, and the longitudinal peak located at 836 nanometers. So after the conjugation, there is a small shift indicated the successful conjugation with the protein. The next step was to use Fourier transform infrared spectroscopy to investigate the successful conjugation of the nanorods with the BSA. And in this figure, there are revealed the spectra for pure gold nanorods, as well as the BSA and BSA conjugated nanorods. In the case of freshly prepared nanorods, there are revealed the bands from around to 29, 24 centimeters and 28 48 centimeters assigned to the alkyl tails of the cationic surfactants. These bands are also presented in the case of conjugated nanorods. Also, in the case of conjugated nanorods, there are presented the specific amide 1 and amide 3 and 2 groups, which demonstrated here. There are the amide 1, amide 2, and amide 3 groups, which are a very specific and clear indicator for BSA adsorption on gold nanorod surface. Going further, we use as I mentioned in the outline of my presentation, we perform several simulations using finite element method in order to investigate which mechanism contributes the most to SPR signal enhancement. And the simulations consisted in a comparison between the responses of SPR signal for two types of sample. The first one with the sensing medium with BSA, and the second one with the sensing medium with conjugated nanorods using console software, multiphysics. Also, there were performed two simulations. The first one without the rod to have a baseline signal, and the second one with the rods, the gold nanorods added at a 10 nanometers distance from the gold layer. And then the distance was increased to 20 nanometers, then 30 and 40 nanometers from the gold layer. Here is the simulated resonance angle variation, the refractive index changes at different cell periodicities, 10, 20, 30, and 40 nanometers. And we observed that by increasing the change in the refractive index, the variation of resonance angle increases for the configuration using the nanorods, which indicates a stronger field confinement at the interface between gold layer of SPR and the nanorods. And for changes between 0.01 to 0.015, the difference between the two signals is very much increased, meaning that the field is more strongly confined at the gold surface when the nanorods are placed on the top of gold layer of SPR. And this difference could be an indicator of enhancement sensitivity for an SPR sensor. Going further, based on these results, there were performed SPR experiments to determine the limit of detection in correlation with different concentration of BSA and BSA conjugated gold nanorods. So there were measurements using different BSA concentration from 100 nanometers down to 10 pico, 100 nanomolars down to 10 picomolars. By increasing the time till 1,200 seconds, and in the absence of gold nanorods, and with gold nanorods, increasing the time till 3,000 seconds. And the lowest, we observed that the lowest detectable concentration was 10 picomolars. In this table, there are shown the concentration and the responses for BSA and BSA conjugated gold nanorods. In the absence of nanorods, the maximum SPR signal was 80.79 for 10 nanometers after 1,300 seconds, and high in the case of conjugated nanorods, a higher SPR signal was obtained with a maximum at 665.93 angle shift at 10 nanomolars, excuse me. So in conclusion, we managed to obtain monodispersed gold nanorods using a seedless method based on a binary surfactant mixture. We evaluated the obtained nanorods using different characterization techniques, scanning, electron microscopy, UV spectroscopy, and we managed to obtain a good correlation between the scanning electron microscopy measurements and the data obtained from UV spectra using gun simulation in order to obtain the aspect ratio of the nanorods. Also, we use the finite element method to explore the potential improvement of SPR signal by adding the nanorods on SPR gold layer. And the obtained results revealed us a stronger confinement of the field at the gold surface when the rods were placed on the top of the gold layer. Also, SPR spectroscopy was used to analyze the changes in the refractive index brought by the immobilization of the unconjugated BSA and conjugated BSA conjugated nanorods. And the results confirmed that the SPR-based detection limit of the molecules with high molecular weight can be enhanced around 10 times by modification with nanorods. Also, this experimental study confirms the possibility of using nanorods to improve limits of detection of the SPR signal. And also, this represents a step towards the low detection limit SPR biosensor, which can be employed in early diagnosis for detecting very low concentration of disease biomarkers represented by proteins. In addition, the future work, we, we we are going to establish the optimum protein goal nanorods ratio and a suitable surface chemistry for an antibody attachment and the detection limit. Once this parameter will be established, this SPR technique could be used as an alternative for COVID detection method. So, thank you for watching me and for your invitation.